Hello, welcome. We're going to be going over chapter 3, which covers both momentum and energy. So let's jump right into it. So, momentum. Momentum is can be described as inertia in motion. It's kind of a hard thing to describe, kind of like if you're trying to describe what color is to someone who can't see. Uh, but you'll see as we talk about it a little bit that you'll kind of get an intuitive feel of what I'm talking about. But the best way to, I guess, to describe it in words is kind of how much something's going to resist slowing down. So once you get something moving, how hard is it to finally get it to stop? Now, the abbreviation for momentum that you'll find in the equations is a lowercase p, and the units for momentum is kilogram meters per second. That will be the unit we're always going to use. And the momentum is equal to mass in kilograms multiplied by velocity in meters per second. So it's pretty easy to calculate, just mass times velocity, and that will give you your momentum. So let's look at a few different aspects of momentum. First, what does momentum depend on? Well, looking at the equation on the bottom left, you can see that momentum is just mass times velocity. So, of course, momentum depends on mass and velocity. Now, how are these things related? Well, if we look at the equation, we can see that momentum, if mass was to increase, then momentum would also have to increase, assuming your velocity stayed the same. So that would mean momentum is directly proportional to your mass. Now, also looking at the equation, we'd see if you increase the amount of velocity while keeping the mass the same, the momentum would also have to increase. So in that case, you can see that momentum and velocity are also directly proportional. And lastly, when would momentum be equal to zero? Well, if an object has to have a mass, because mass is just a measurement of how much stuff something is made of. So if you have an object, it has to be made up of stuff, I guess, unless it's an imaginary object or something like that. But it's going to always have a mass. So if it has to have a mass, the only way to have momentum equal to zero is if velocity is equal to zero. So if you have no velocity, then you're going to have no momentum. So let's jump right into an example. How much momentum does a truck with a mass of 10,000 kilograms have if it's moving at 10 meters per second? So we're going to need the momentum equation. Now it's easy to be able to pick this equation out because they're asking us about momentum and they're telling us a mass and a velocity. So if you looked over all the equations, you could find there's only one easy equation that has momentum, mass, and velocity all listed in it. So once we have that equation, it's pretty easy to plug in our numbers of the 10,000 for the mass and the 10 for the velocity, and we'll get a total momentum of 100,000 kilogram meters per second. So this is a pretty easy concept to work with dealing with math. So as I said, momentum is directly proportional to mass and and also directly proportional with velocity. So you can kind of imagine this pretty easy. What's harder to stop? A little kid on a tricycle or a bus if they were moving at the same speed? Of course, the bus would be much harder to try to stop uh, because it's got a lot more mass, so therefore it would have a lot more momentum. Now, several times during this class, we're going to use the word conservation, and then I'm about to talk about it in the first time here in a minute. So let's kind of talk about what I mean when I say conservation. So what it really means is whatever you have before, you also have after. So probably the first thing that came to mind when I mentioned conservation was the idea of saving the environment, maybe conserving the rainforest, for example. So if we're talking about conserving the rainforest, what we're really talking about is uh, trying to keep the number of trees still there. You don't want to go, cut down all the trees or anything. So let's say we had someone going to cut down a few trees to make paper or a lumber mill or something like that. So let's say every time they cut down a tree, the lumber mill or whatever, they plant a new tree in its place. So they cut down 1,000 trees, but they plant 1,000 trees. So the total number of trees would be the same before they showed up and after they showed up, because every one they cut down, they also replaced it. Now you could argue that the new trees are smaller or something like that, but just if you're looking at the number of trees, that would be the same. So then you could say that the number of trees was conserved because before and after was the same number. So that's what we're going to use conservation to mean. The amount before and the amount after is not going to change. So the first thing we're going to talk about that is conserved, surprise, surprise, is momentum. So conservation of momentum states that in the absence of some external force, the total momentum of a system remains unchanged. But we're going to mainly be talking about collisions. Now, this whole external force thing basically means if you calculate your momentum for, say, a couple billiard balls, the total momentum for those two billiard balls is not going to change unless there's an external force. So if someone walks by and like thumps one of them or gets in the way, hits it with a pool cue, something like that, that's going to change the total momentum. So conservation of momentum only works as long as there's nothing on the outside messing with it. No, we're not going to ever have to deal with a case. We're going to have something on the outside messing with our problems. So you can always assume that conservation of momentum will work. We're not going to ever try to throw any monkey wrenches into the deal and to mess this up. Now, there's two different types of collisions. There's elastic collisions and inelastic collisions, and we're going to talk about them individually. So the first type of collision is elastic collisions. This occurs whenever two objects collide and then bounce off of each other. Now, how I like to imagine elastic collisions are two rubber bouncy balls. So you have two super balls or bouncy balls. If they hit each other, they're just going to easily bounce off of each other. Or if you take a bouncy ball and throw it up against the wall, it's just going to bounce right off. So that, in my mind, I think of elastic and rubber, so that works as a way to remember it. Another good example of elastic collisions would be pool balls, because when they hit each other, they just bounce off. So in elastic collisions, the momentum before the two objects collide is going to be equal to the momentum after the two objects collide. So using this idea that momentum before equals momentum after is going to allow us to do some cool tricks on figuring out what's going to happen if two things hit each other. So if I said momentum before equals momentum after, and I've already said momentum is mass times velocity. So if we take the mass of one object times the velocity of that object, that would be the momentum of the first object, and add to that the mass of the second object times the velocity of the second object, which is just the momentum of the second object. If we add those two together, then we'll have the total momentum before the collision. Now that's going to equal the momentum of the first object plus the momentum of the second object after the collision. So it will be m1v1, mass of the first object, mass of the second, or mass of the first times velocity of the first, plus the mass of the second times the velocity of the second. And if that's still a little bit fuzzy in your mind, just let's go through an example and you'll see exactly what I'm talking about. So let's say we have two carts. They're both going to have a mass of, the first one's going to have a mass of 2 kilograms, and it's going to be moving at 5 meters per second. The second cart, the red cart, is going to have a mass of 1 kilogram, and it's sitting still, so it has a velocity of 0. Now the blue cart, the larger cart, is going to move in, hit the red cart, and then the blue cart's going to stop, and then the red cart is going to start to move. And the question is, how fast will the red cart be moving after they collide and the red cart gets knocked off? Okay, so how we do all these collision problems is to start off by looking at before the collision. So we're going to focus only on before the collision. So they haven't hit yet. So before the collision, we can look and find out what the total momentum is. That's what we're really looking for, because if we know what the momentum is before they collide, we'll know what the momentum has to be after they collide. Now, the only way to find the total momentum is to find the momentum of each individual cart and combine them. So let's start off with the momentum of the blue cart. So momentum is mass times velocity. So the mass of the blue cart is 2 kilograms. The velocity of the blue cart is 5 meters per second. So plugging those in, and we find that the momentum of the blue cart is 10 kilogram meters per second. All right, now for the red. Well, the red cart still has the same, momentum equals mass times velocity. So I'll plug in its mass of 1 kilogram. It has a velocity of 0. So the total momentum of the red cart is 0 kilogram meters per second. But of course, we should have already known that without the equation, because we already know that if something's not moving, it can't have a momentum. So now for the total momentum, all we have to do is combine the two individual momentums. So the momentum of the blue cart plus the momentum of the red cart. So that's 10 plus 0, which gives us a total momentum of 10 kilogram meters per second. Now, if the red cart had something other than 0 momentum, like it had a momentum of 5, then you just add the 10 plus the 5. Now, you would do that if they were in the same direction, because momentum is a vector, so direction is important. So just like when you were dealing with forces from chapter 1, if you have two forces in the same direction, you add them together. If you have two forces in opposite directions, you take the big one and subtract the small one. So momentum's the same way. If you have two things with this, momentum and they run into each other, if they're going the same direction, you add them. If they're going in opposite directions, you subtract them. But in this case, 1 is 0, so we don't have to worry about that. So the total momentum before the collision is 10. So let's look at after the collision. So what is the total momentum after the collision? Well, we should already know that answer because it's the exact same as the total momentum before the collision. So we already calculated that to be 10 kilogram meters per second. All right, so let's look at the individual carts again. Now this is after they collide, so the numbers are going to be a bit different. So momentum of the blue cart. Momentum is still mass times velocity. We're using the equation a third time. So momentum will give us, the mass is 2 kilograms. Now after the collision, the blue cart is not moving, so now its velocity is 0. So the total momentum of the blue cart after the collision is 0. Well, let's think about this for a second. If we know the blue cart's momentum plus the red cart's momentum has to be 10, and the blue we already know is 0, we know the momentum of the red cart has to be 10. That's the only other thing that you can add to 0 to get 10, of course. So if we look at the red cart, we know the momentum of the red cart has to be 10. So we can put 10 in for its momentum. So 10 is going to equal its mass times its velocity. So plug in our mass of the red cart as 1 kilogram, and we're trying to solve for velocity. So at that point, you divide both sides by 1, and we get a final velocity of 10 meters per second. So that's how fast the red cart is going to go after they collide. So that's where this whole equation's coming from that I showed you before. It seems very complicated, but all it's really saying, it's the momentum of the first cart plus the momentum of the second cart before they collide has to equal the momentum of the first cart plus the momentum of the second cart after they collide. So it's really not that complicated, but you do have to kind of break the problem up and solve before the collision and then do some stuff after the collision. So it takes a few steps to solve it, but the math is not very difficult. So the second type of collision is an inelastic collision. This is what happens whenever two objects collide and they stick together. So as soon as they stick together, you know it's an inelastic collision. You can also identify inelastic collisions if the two objects collide and they get deformed. So imagine two balls of clay. If you were to throw them at each other, they would flatten out a little bit and they would stick together. That would be an inelastic collision. You could also have a car wreck where two cars hit each other, and then when they smash into each other, they're deforming. So that would make it inelastic, and they're most likely going to stick together a little bit as well. So those would be inelastic collisions. Now, in inelastic collisions, momentum is still conserved. So momentum before will equal momentum after. So these problems are solved in a similar manner. So let's look at an example of it. Say we have a 500 kilogram cart moving at 10 meters per second, runs into a second 500 kilogram cart that's sitting still, and they lock together. So let's say they're train cars or something like that. So as soon as they hit, they get latched together. We want to know what would be the velocity of the two cars after they're attached. So after they hit, they're going to move together as one large cart. So again, we're going to start by looking at before the collision. And we'll ask ourselves, what is the total momentum? Well, in order to find the total momentum, we need to find the momentum of each individual cart. So we're going to start with the green one. Momentum is mass times velocity. So mass of 500 kilograms, velocity of 10. So the total momentum of the first green cart is 5,000 kilogram meters per second. So now looking at the momentum of the purple cart, still mass times velocity. So it's 500 times 0. So the momentum of the purple cart is 0. So the total momentum is 5,000 plus 0, which gives us a total momentum of 5,000 kilogram meters per second. Easy. So now that we know that, we can jump over to after the collision. And what's the momentum after the collision? Of course, it's the exact same number as before, 5,000 kilogram meters per second. And now we have to look at the momentum of both of the carts. Now we're going to be using the equation momentum equals mass times velocity again. But before we write that down, let's think about this mass that we're going to be using. So now we're looking at both carts combined as though they were one large cart. They're one object now. And if we know mass is just how much stuff something is made of, if you have one cart and you stick it to the other one, and they both have all the mass that was in the first one and all the mass that in the second one are getting mixed together or getting combined. So the mass of the new large cart, the stuck together cart, is just going to be the same as the mass of the individual carts added together. So I'm going to put that in with our momentum equation. So the total momentum is going to equal the mass of the first cart plus the mass of the second cart, because now they're stuck, and times the velocity that they're going to move afterwards. And there's only one velocity, of course, because they're moving together. So we know what the momentum has to be. The momentum has to be 5,000. So I'll plug in 5,000 for the momentum. The individual carts both have a mass of 500, so I can plug 500 in for both of those masses. And of course, we don't know what the velocity is. All right, so 500 plus 500 gives us 1,000. And then we divide both sides by 1,000 to get velocity by itself. We get a final velocity of 5 meters per second. So that will be the speed at which the combined carts are going to move after the collision. So you see, both ways are solved almost the exact same way, but there's just a small amount of change whenever you're dealing with the fact that the two objects are stuck together in the end for inelastic collisions. So we have basically the same equation before. The momentum of the first object plus the momentum of the second object before the collision is going to equal the total mass combined times the speed after the collision, so the momentum afterwards. All right, so now we're going to move on to force. We're going to slowly make our way over into talking about energy. But before we can talk about energy, we need to touch very briefly on work. And work has a slightly different definition of what you're used to. Force has got a very particular physics science definition, and this work does not, doing physics homework does not count as work as far as this equation goes. Now the units of work is the joule, and it can be abbreviated with just a capital J, and it's calculated by taking a force that is applied to an object in newtons multiplied by the distance that that object moves in meters. So work equals force times distance. So work can be described as work is done on an object whenever a force succeeds at moving an object some distance. So two things have to be in place in order for work to be done. An object has to have a force applied to it, which is just a push or a pull, and that object has to move. If you don't have both of these things, you don't have work. So let's look at a couple of examples. A student applies a force to a wall and becomes exhausted because they're pushing on the wall all day long. Does this count as work? No, it doesn't. And why not? Well, there is a force, but the wall doesn't move, so there's no distance being traveled. So we have no work being done. A man lifts a brick into the back of a pickup truck. Is that work? Yes, it is. And why is that? Well, you're putting a force, you're lifting the brick up, and the brick moves. So you have work. A book falls off a table and is in free fall until it hits the ground. Is there work? Yes, there is. We've got force, in this case gravity, pulling the book down, and the book moves, it's falling towards the ground, so of course work is happening. And lastly, a waiter carries a tray full of meals above his head by one arm, and he's walking across the room. Is work being done? No, it's not. Now the waiter is pushing up on the food when gravity is pulling down, but the plate's not moving up or down, right? So the waiter is pushing up, but that upward force is not causing the plate to move across the restaurant or whatever, because he's pushing up. That upward force is not what's causing the plate to move across the room. So the waiter pushing the tray up is not an example of work. You can look at, if you want to look at it in the horizontal direction, how the plate is moving horizontally, then what you'll end up having in that case, because the waiter is moving at a constant speed, the net force on the tray has to be zero, because the tray of food is not accelerating or decelerating. So because there's no net force in the horizontal direction, then even though it's moving, you don't have any work being done because there's no net force in the horizontal direction. All right, so how much work needs to be done to accelerate a 50 or 500 kilogram object 3 meters per second squared to 2 meters? So how in the world are we going to solve this problem? Because we can't just glance at the momentum equation and immediately see the answer. But we'll see how this comes about in just a moment. So the first step whenever solving any of these difficult math problems is to start off by writing down what you know. So what does the problem tell us? Well, they tell us we have a mass of 500 kilograms, we have an acceleration of 3 meters per second squared, and a distance of 2 meters. So step 2, what is the problem asking us? Oh, and we've got a typo. It should say, what is the work? Or how much work? That the question changes on me. All right, so we're going to ignore the question for this slide. It should be the same question as the previous slide. All right, so the question was asking, what is the work? Now, we can look to see what equations we need to use, and we can find the work equation as work equals force times distance. But if we go back to step 1, we can see that we have a distance but we don't know the force, at least not yet. So we're going to have to do a little bit more work. We need to find out what the force is going on here. Well, we can look at the equation sheet and find out what equations can tell us how to calculate force. And we can quickly find that force equals mass times acceleration. Well, we have a mass and we have an acceleration, so we can replace force with mass times acceleration, which is what I've done here. So work is going to be the mass times the acceleration, which gives us the force, that times the distance of 2 meters, and that will finally give us the total work. So the total work in this case is going to be 3,000 joules. All right. How much work needs to be done to lift a 500 kilogram object 2 meters in height? Well, we know work equals force times distance. Again, the same equation popping up over and over for work. But now let's think about this for a second. Now we're lifting an object up, so the distance is pretty easy to figure out because we're lifting it a height of 2 meters, so the distance that the object is moving is 2 meters. It just happens to be lifting it up, so we call it height, but it's still just a distance. Now this force plays is a little bit trickier though, because all we're given is a mass. We're not given a force. But when you're lifting something up, how much force do you have to apply to make that object go up? What are you having to fight against? Of course, you're having to fight against gravity. So in order to make something go up, you have to put a same amount of force as the object's weight. The weight is how hard it's being pulled down due to gravity. So the force for any problem dealing with work, where we're having to lift something up, is going to be the weight of the object. That's what you're having to fight against to make the object go up. Now we can look on the equation sheet and see that weight equals mass times gravity. So I can replace force with weight. And of course, weight is just mass times gravity. So the total amount of work is mass times gravity times the distance. So we plug in our mass of 500 kilograms. G is 9.8 meters per second squared, at least here on Earth, which you can always assume you're on Earth unless a problem specifically tells you otherwise. And the distance is going to be 2 meters. So plugging in all those numbers, and you quickly get the total amount of work as 9,800 joules. Now, if we're wanting to look at how quickly you're doing work, what you'd be talking about is power. Power is how much work is being done per unit time, or just how quickly you're doing work. You're probably most familiar with work in the using work in terms of horsepower. If you're looking at how much like horsepower your car has, that's how quickly your car can do work. So power, the units of power is a watt. And yes, this is the same watt that's in your light bulbs, if you're talking about like a 60-watt light bulb. But we'll talk about that more when we talk about electronics in a later chapter. So our power is going to be in watts, and it's just the total amount of work in joules divided by how long it took for you to do the work, and time in seconds. So it's just work divided by time will give you power. So another pretty easy to calculate value. So because that's so easy, and you've had lots of chances to practice such a very simple equation, let's jump into something a little bit more involved. How much power is needed to accelerate a 2,000 kilogram car 5 meters per second squared, a distance of 200 meters in 10 seconds? Well, that's just a whole bunch of stuff thrown at you all at once. So let's break it down a little bit. All right, power. There's only one equation on the whole equation sheet that has power in it, and that's going to be power equals work divided by time. So we're going to need this equation. But let's look at what the problem gives us. Well, we don't know what power is, of course. That's what the question's asking us. They tell us what the time is a time of 10 seconds, so we're good there. But we don't know what work is. They don't tell us what the work is. Uh-oh. Well, we're going to need a second equation because we need to figure out what the work is. Well, looking on the equation sheet, we can find out that, of course, work equals force times distance. So I'm going to replace work with force times distance. All right, so looking at the equation, what the problem gives us again, we have a distance of 200, but we don't have a force. We're going to have to go and find another equation because all we have is a mass and an acceleration. But of course, at this time, you're probably quite familiar with the idea that force equals mass times acceleration. So we can replace force with mass times acceleration. So the mass of 2,000 kilograms times the acceleration of 5 meters per second squared, which gives us the force, multiply that by the distance of 200, which that total value then would give us the work, divide that by the 10 for the 10 seconds, put all that into our calculator, and we get our power. So our total power is going to be 200,000 watts. So that's quite a bit of power. So that's about as most difficult of a problem you're going to get like this, where you have to use a couple different equations in order to find your final answer. But if you take things slow and write everything down and think about it for a little bit, you'll find that this is really not that complicated as long as you don't panic. Just calm down, relax, write everything down, and you can kind of do it step by step and finally get down to your answer. So now that we're prepared with math, work, and power, we can jump over and really start hitting energy on a little bit. So what is energy? Energy is a weird thing to try to define. It's some stuff that changes matter. And it can't be created or destroyed, but it can change forms. There's lots of different types of energy. And you can really only observe it whenever it's going from one place to another place, or whenever it's transforming from one type of energy to another type of energy. The rest of the time, it's just kind of hidden there and you don't really notice it. Now, energy is also measured in joules, just like work is measured in joules. So here's a few different types of energy. There's a lot more than this. There's thermal energy, which is heat. Got acoustic energy is sound. Magnetic energy is energy stored in magnetic fields. Electrical energy, of course, is electricity. Mechanical energy is movement. Chemical energy is chemical bonds. But there's a whole bunch more. So let's look at this idea of energy being conserved and not being able to be created or destroyed. So how does this exactly work? Well, let's start off looking at a sun, or our sun in that matter. In the middle of the sun, you see all this light coming off of it. So where is this energy coming from? Well, what a sun is doing is using a process called fusion, which is basically taking two individual atoms, like usually hydrogen atoms, it squeezes them together to make a heavier atom. So if you squeeze two hydrogen atoms together, you would end up with a helium. Now, in the process of squeezing these two atoms together, some of the mass, some of the stuff that makes up these atoms is lost and is transformed into energy. You can actually calculate how much energy would be created by using the very famous E equals mc squared equation. So this equation, even though you're not going to do any problems with it, this is kind of extra information, that E is energy, it's energy in joules, equals the mass of the object that got turned into energy in kilograms, multiplied by the speed of light squared. The speed of light in a vacuum, that's 300 million squared. So it's taking mass and turning it into energy. The type of energy it's turning it into is photonic energy, which is light energy. So that light energy travels from the sun, takes about 8.5 minutes, and eventually lands on Earth. So when that light lands on Earth, some of that light's gonna, let's say, run into a tree. And that tree is going to use photosynthesis to turn that light energy into chemical energy. But it's still the same energy that was made by squeezing the atoms together. Same energy that was the light, it's just getting turned into chemical energy. Well, now a dinosaur comes over. He munches on the tree a little bit, and it takes that chemical energy and is able to put that chemical energy inside of its muscles, and the muscle will turn the chemical energy into mechanical energy. So that's basically what muscles do. They take chemical energy from the food you eat and change it into motion, makes your arms move and allows you to talk and everything else. But of course, you eat a whole bunch of stuff and you store some energy in your body, so you're not going to use all of it. So let's say a asteroid comes down, crashes and destroys the poor dinosaur. I'm sure he did think, oh no, as he saw it coming in. Millions of years pass by, and eventually the dinosaur turns into coal. So this coal still has the chemical energy that the dinosaur got from the tree, that got its energy from the light. The light got its energy from the fusion. Well, that chemical energy gets harvested in the form of coal, sent over to a power plant, and is converted into electrical energy. So now we're converting chemical energy into electricity. Then we could send that electricity all over the world, and some of it might end up in a maglev train. Then you'd use that electricity to make powerful magnetic fields. Now, the magnetic fields allow the train to float above the track and allows the train to move forward. But of course, that magnetic energy came from the electrical energy, that came from the chemical energy, that came from the photonic energy, which came from fusion. And lastly, as the train moves on, it's going to make a lot of noise. It's going to have lots of air resistance, make a lot of friction. That's going to be acoustic energy and thermal energy. So all that energy that went into the magnetic fields is going to turn into other types. So you see that the energy is just moving from place to place to place, and it's changing from type to type. It's not getting created or destroyed, just moving around. Now we're going to focus on two different types of energy. The first type is potential energy. Potential energy is defined as energy stored in something due to the position, shape, or state of that object. So how it's positioned or where it's sitting is going to determine its potential energy. So for example, if you pull back a bow and arrow, you have like a bow, it's going to have potential energy. Or if you stretch a rubber band, it has potential energy. Now, we're going to mainly focus on one type of potential energy, and that type is called gravitational potential energy. That is potential energy that an object has based on coming from the gravity that's pulling it down. So it's kind of based on how high above the Earth that object is. So potential energy, which is on the equation sheet, is a capital P and an E together. It's the units of potential energy is in joules, like all forms of energy. And it's pretty easy to calculate by finding the mass of the object times g, which is the acceleration due to gravity, or 9.8 meters per second squared, times the height of the object in meters. So it's mass times gravity times height, and that will give you your potential energy. Now you'll notice on that equation that the only thing that really mattered, is we need to know the mass and we need to know the height. And of course, we're going to assume we're on Earth. But it never talks about how the object gets to that height. So in this picture, you can look at moving this green ball like straight up a wall, or moving it up a ramp, or moving it up a steps. In all three cases, it ends up 3 meters above the ground. So in all three cases, it's going to have the exact same amount of potential energy. Now, something else that's interesting, if you were able to do all the calculations for it, you would find out that it took the same amount of work to move the ball from the ground up to that same height. Now, what this is actually telling us is, it's telling us another way to describe what work is. What work does, it gives or takes away energy from something. That's why work had the units of joules, because it's giving energy or taking away energy. So if you're doing work to lift something up in the air, what you're doing is you're using that work to give the object potential energy. So let's look at an example. How much potential energy does a 25 kilogram mass have when it's lifted to a height of 2 meters? And then we can also look at how much work it would take to lift that 25 kilogram mass up to a height of 2 meters. So first, potential energy. Potential energy is mass times gravity times height. So we have 25 kilograms times 9.8 times 2, and we get a final answer of 490 joules of potential energy. That's pretty easy to solve. So now let's solve the same thing, but let's look at how much work it takes to lift up the object. So work equals the weight times the distance. Now, work normally means force times distance, right? But of course, we're lifting the object up. So the amount of force that we're using is equal to the object's weight. So we have to use weight for the force. And we know weight is mass times gravity. And the distance that the object is lifting it up is that height, that 2 meters. So we plug in our mass of 25 kilograms. We turn in G, plug in G for 9.8. The height of 2 meters, that's how far the object moved. So again, we get work equals 490 joules, which makes sense. So we did 490 joules worth of work to lift up the 25 kilogram mass 2 meters. So of course, the total potential energy it should have will be the 490 joules. That's what we did with the work. We did work to give the mass potential energy. Now we can look at the second type of energy we'll talk about today, which is kinetic energy. Kinetic energy is the energy of things moving. In particular today, we're going to look at kinetic energy in the form of things moving back and forth. So moving in a straight line. You can also have kinetic energy in the form of things spinning, but we're not going to worry about spinning today. We're just going to worrying about, let's say, how much kinetic energy does a car have when it's driving down the road, that kind of thing. So kinetic energy, which abbreviated with just the KE, also has units of joules, like all forms of energy. And it is equal to 1/2 times the mass of the object times the velocity of the object squared. So be very careful to not forget your squared on this equation. That's one of the easiest ways to get a kinetic energy problem wrong, is you forget to square the velocity. Now here we get to see that we can see that kinetic energy is exponentially proportional to velocity. So we already learned a little bit about kinetic energy before, but it's really easy to spot because we see since the velocity is squared, that means kinetic energy and velocity must be exponentially proportional. So a small change in your velocity could end up making a very large change in your kinetic energy. So we can look at this in an example. How much kinetic energy does a 10 kilogram object have while moving 10 meters per second? So kinetic energy is 1/2 times mass times your velocity or your speed squared. So we can plug in our mass of 10 kilograms, our speed or velocity of 10 meters per second. We have to square that. So putting all that into your calculator, you'll find that the total kinetic energy is 500 joules. All right, so that was the first way of solving it. Now let's change this problem up a little bit and see what happens. So we're going to do the exact same problem again, except now we're going to use twice as much mass. So while before we used 10 kilograms, now we're going to use 20 kilograms instead. So we're going to do 1/2 times 20 times 10 squared. So plugging all that into your calculator, you'll eventually get down that the kinetic energy is 1,000 joules. So before, the kinetic energy was 500, but after doubling the mass, the kinetic energy also doubled. So we can see that kinetic energy and mass are directly proportional because we doubled one and the other one also doubled. All right, so let's do that first problem again, but this time we'll double the speed instead. So we'll leave the mass at 10, and now we'll use a speed of 20. So 1/2 times 10 times 20 squared. So now plugging that into our calculator, we'll find that the kinetic energy equals 2,000. So we doubled the speed from 10 to 20, but the kinetic energy went from 500 to 2,000. So the kinetic energy got 4 times larger. So because it got 4 times larger while the speed only doubled, that shows us that kinetic energy and speed must be exponentially proportional to each other. Now, I already gave it away, but energy is conserved. So the total amount of energy you have in some system has to equal the total amount of energy you have after something happens in that system. So the energy can change forms, but it can't vanish. Okay, it can only move around a little bit. So we're going to use conservation of energy to solve a couple problems here. Now, when we're talking about an object dropping, and we know that if all we're going to deal with is an object falling, the only two types of energy we need to worry about are potential and kinetic energy. And if we have conservation of energy, that means the total energy, which is the kinetic energy plus the potential energy of some object, has to stay the same. So let's see what I'm talking about here. So let's look at this little smiley face. He's standing on top of a cliff, and he's happy up there. That's why he's smiling. And let's say we did a few calculations, and we found out that he had a potential energy of 10 joules while he's on top of that cliff. And he has 0 kinetic energy. That's because he's not moving. He's just sitting still. So his total energy is his potential energy plus his kinetic energy. So his total energy is 10 joules. All right, so now he jumps off the cliff. And he falls a little ways, and then we're going to freeze time for a second. So now at this point, he's fallen a short ways, so he's not as high up as he once was. So if he's not as high, his potential energy has to be less, because his mass is the same, he's still on the same planet, so if his height is less, his potential energy has to be less. But we know the total energy has to be the same, because there's conservation of energy. So if his potential energy went down by 3 joules, his kinetic energy had to have gone up by 3 joules, so they stay added together, equaling 10. So then he travels a little bit further down, we freeze time again. Now he's getting close to the bottom. Now he's not at the ground yet, so he still has a little bit of potential energy. Now in this case, he only has 2 joules of potential energy. But he has a whole bunch of kinetic energy now. He's going to have 8 joules. So the 8 joules of the kinetic plus the 2 joules of the potential still add up to 10. And that makes sense because the longer you fall, the faster you're going to be moving. And if you're moving faster, you're going to have more kinetic energy. All right, so lastly, we're going to freeze time right as he is starting to touch the ground. So like he's touching the first little grain of sand. He hasn't slowed down yet. He hasn't made a crater just as he's about to touch the ground or just as he's touching it. At this point, he has a height of 0. So if he has a height of 0, he has 0 potential energy. So if he has 0 potential energy, he must have 10 kinetic energy. So all the potential energy he had at the top of the cliff, that 10 joules, all eventually changed into kinetic energy at the bottom, where he has 10 joules of kinetic energy. So whenever you have something that's starting at rest and then goes into free fall, the amount of potential energy he has before he started to fall is going to be the exact same as the amount of kinetic energy they have when they hit the ground. It's just going to transform all the potential energy into kinetic energy. So these two things are always going to be equal. Potential energy at the top of a cliff and the kinetic energy that the object will have at the bottom right before it hits the ground. This is basically how roller coasters work, or at least most of them. They start off in the roller coaster, they drag you up to the top of a very big hill. So what they're doing is giving you a whole bunch of potential energy. So then as you start to roll down that hill, you lose potential energy but gain kinetic. So let's follow this cart as it starts to roll down. These charts on the right, see how that blue line shows it has a lot of potential, and as it drops, it's gaining kinetic. It gains all that kinetic, then it starts to lose kinetic as it goes up, but gain potential, and then vice versa. So by watching those two bars, you can see it goes from one to the other, from one to the other. The potential turns into kinetic, and then the kinetic turns back to potential when it goes uphill. Now the TME bar, that's the total energy. You'll see the total energy never changes. It's just changing from potential to kinetic and back and forth. Now, this only works perfectly whenever there's no friction. If there's friction, that's another form of energy. So you'd have to take that into account as well. This example only is assuming there's no friction. So let's think of another example of how potential and kinetic energy can interact with each other. So let's imagine a bow and arrow. They're doing a little bit of archery here. So imagine you're holding your bow and arrow. You grab the string, then you pull the string back, stretching it as far out as you can. So what you're doing is you're applying a force on the string of the bow, and the string of the bow is moving. So what are you doing? You're doing work. You're applying a force, and the string is moving a distance. So you have force times distance, so you're doing work. And that work that you're doing is giving the bow potential energy. It's holding that potential energy in the springiness of the arms of the bow. So now you put your arrow on the string. Well, you probably already had the arrow on the string. And then you let the string go. So now the string is going to start pushing the arrow forward. And all that potential energy that was stored in the bow is going to be given to the arrow in the form of kinetic energy. So all the potential energy in the bow gives that arrow kinetic energy. So if the arrow has kinetic energy, that means it must be moving. And it's probably going to be moving fast. So the more potential energy the bow holds, the more kinetic energy the arrow will have. And therefore, the faster the arrow will be moving. Now we've talked about two different things that are kind of similar to each other, but have some important differences. And these two things are kinetic energy and momentum. Now, both kinetic energy and momentum depend on mass and velocity. Momentum is mass times velocity. Kinetic energy is mass times the square of velocity. Now, these two, even though they're somewhat similar because they both have mass and velocity in their equations, they are two very different things. You need to try to keep them separate in your mind. Momentum is a vector quantity, so it has a direction, while kinetic energy, along with all forms of energy, are scalar quantities, so it's just an amount. It's not a direction. So just try to keep those two things separate in your mind. They're not really the same thing, even though they both have mass and velocity in their equations. So these are all the equations we've talked about today, along with a picture or in words how you would say that equation. So like this first equation, it's force equals mass times acceleration, and there's what it looks like in math symbols. So you can kind of look at those and see how you would say them if you have trouble with that kind of thing. And that covers it for all of chapter 2. I hope that everything was clear for you, and good luck on your assessment.